Hello all, welcome to the Basics.Academy. This is Smart Contract Security, Fundamentals and Auditing, a 5 units, 3 credit course in the BSc Blockchain Technology program. Let's get into it. Today we are going to talk about error handling and gas optimization, in which we will look into require, assert, revert, then get into the depths of custom errors, gas stipends, and storage packing. Require, assert, and revert are Solidity's state reversion mechanisms. Whenever you perform a transaction, that transaction updates the blockchain state. The state goes from S0 to S1 to S2 and so on. However, as soon as either of require, assert, or revert is encountered, that leads to the state updates to be reversed. Hence, require, assert, and revert are Solidity's state reversion mechanisms. Custom errors were introduced after Solidity 0.8.4. Custom errors are cheaper and are the alternatives for string-based require messages. Then going ahead, we will look into gas fundamentals and the transfer or send trap. Why a hard-coded 2300 gas stipend is now a liability, not a safeguard. At last, we will look into storage packing, in which we will have a look at fitting multiple small variables into a single 32-byte storage slot. Today's theme would be failing safely costs gas and gas has a price. Every construct we cover is a trade-off between clarity, safety, and cost. Let us now look into when to use the require statement. Require is used for validating inputs and conditions. It is used for validating inputs and conditions. What it does? It reverts all state changes. If require statement is encountered and the condition fails, then whatever the state updates were done prior to this, everything is reversed and the unused gas is returned to the caller. The unused gas is returned to the caller. Apart from that, require also returns an optional string message. Now this optional string message can be shown on the front end to the user, which would make him or her understand what exactly has went wrong at the smart contract level. For what purposes one must use require? Require must be used for conditions that depends on external input, such as user supplied values or return values of external calls. The mental model one should keep in mind when it comes to require is require, then the condition and the optional error string message. If this condition fails, the smart contract will return this error string message. Next is assert. Assert is used for guarding internal invariants or condition that can never be false. For example, in the given mint function, the total supply gets incremented by the amount and the balance of the receiver is also incremented by amount. Then at last, we assert that the total supply must always be greater than or equal to the receiver's balance. This should be mathematically impossible to violate. Or when this condition fails, it implies that something is deeply wrong in our own logic and not related to Solidity. So, assert basically guards internal invariant or condition that should always be true. And the last state reversion mechanism is revert. Revert is explicit and unconditional failure. It is unconditional counterpart to the require statement. What is meant by this? Require takes a condition and whenever this condition evaluates to false, then require internally reverts the transaction. However, in case of revert, there are no conditions. All revert takes is the message and then it reverts the entire transaction. Let us take a look at an example. Here we check if the caller is not the owner, then we revert saying caller is not the owner. In the second if block, we check if the new owner is equal to address 0, then we revert with the message new owner cannot be the zero address. Hence we say that revert is unconditional failure. All revert takes is the error message to be returned to the caller. It has the same refund behavior as require. That is, whenever a revert statement is encountered, whatever gas is remaining, that is refunded to the caller. It is best for multi-branch validation logic or reverting with a custom error. In next slide, we are going to look into custom error. In order to revert with custom error or return custom error, one must necessarily use or make use of the revert keyword. Let us now compare require, assert and revert on the basis of use case, the error type, the behavior when it comes to failure, then the typical source of bug it signals. The mental model to remember in case of require is require takes in a condition. If this condition evaluates to false, then it returns a message to the caller wherein the message is specified after the condition. In case of assert, assert only checks the condition, and then in case of revert, revert only returns the error message. What is the use case for require? Require is used for input or access checks. Assert is used for internal invariants that should never be false, and revert is unconditional or multi-branch failures. What happens when we encounter a require statement? What happens to the gas? The unused gas is refunded in case of require. In case of assert, the unused gas is refunded only after Solidity compiler version 0.8. Prior to that, the unused gas was not refunded to the caller. In case of revert, this exhibits the same behavior as require, that is, the unused gas is refunded to the caller. What are the typical source of bug it signals? In case of require, it signals bad caller input or the input arguments provided were not as expected and some conditions were not satisfied. In case of assert, it signals there is a bug in the contract's own logic. And in case of revert, it is same as require, but it is a structural choice. Either you can go with the require statement or using the revert option. What is the memory hook that one must remember? Require and revert, these are conversations with the caller. That is, you did something invalid. Whereas assert is the contract talking to itself. That is, I broke my own promise. This is the mental hook or memory hook one must remember when it comes to require and revert as compared to assert. Custom errors were introduced starting from Solidity version 0.8.4. Prior to 0.8.4, there were no custom errors. How to define custom errors inside the contract? Custom errors are defined using the keyword error followed by the name of the error and in parenthesis any arguments that you want to return to the caller. How custom errors are emitted or sent back to the caller? Here inside withdraw function, we are checking this condition. If the caller is not the owner, revert with not owner, pass in the caller and the actual owner address. Hence, to make use of custom errors inside your contract, you must use the revert keyword followed by the custom error name and the argument it expects. Let us take a look at the second if statement or if block in which we check if the balances of the caller is less than amount, then we revert or throw a custom error insufficient balance with the amount and the actual balance of the caller. This is how you make use of custom errors in Solidity after version 0.8.4. One thing to remember is the error keyword, the error name, and the arguments that you want to return to the caller. Let us now try to answer this question, why custom errors cost less? The idea is simple. If you can do a task in 3 steps as compared to a task that can be done in one step? Obviously, the answer is whoever is doing the task in one step will cost less. So prior to custom error, we were using the require statement. Whenever the condition fails, we return an error string message. So what happened? This full string, caller is not the owner. This was encoded into the deployed bytecode and it was recopied to memory on every field call. Right? It was recopied to memory on every field call. However, after the introduction of custom error, what happened? It only returns a 4-byte selector. This is like a function selector which is stored and emitted, no string data at all. So earlier, this entire string was encoded into the deployed bytecode, and whenever this condition evaluated to false, this was recopied to memory on every failed call. After the introduction of custom error, all we have to return or all that we are returning is a 4-byte selector, and this 4-byte selector is nothing but the function signature or the error signature. So what is the net effect? Smaller deployment bytecode that leads to lower one-time deployment cost and lower runtime cost on the failure path with typed parameters as a bonus for anyone consuming the error off chain. What is meant by this last line? It implies these are the typed parameters. This can be consumed off chain by the DApp frontend. Gas fundamentals. What actually costs gas? Whenever you are trying to load a variable from the smart contract storage, the relative cost is high. The reason being, storage is permanent on-chain state and every node must persist it. The second instruction that takes the highest gas is SSTORE or writing to storage. Now this is the highest, especially when you are changing a 0 value to a non-zero value. What does it mean? Let us say initially the balances mapping in the storage was 0 for address 1. Now when you are updating that balances mapping to say 100 for address 1, so the first write will be the highest because writing new state is the most expensive class of EVM operation. Then we talk about memory operations. The relative cost of memory operations is low. Reason being, they are temporary, scoped to the current call, and they are erased afterward. For instance, when we invoke the withdraw function, whatever variables we will be using inside the withdraw function, those will be erased after the withdraw function successfully executes. So those variables are loaded into memory and their cost is relatively low. Then at last we have call data. Its relative cost is the lowest and it is not written to state at all. It is just the bytes attached to the call. Also, it is recommended to use call data whenever you are passing function arguments via a function whose visibility is external. One thing to keep in mind, or one must always remember, is the core optimization principle is minimize storage writes, prefer memory or call data wherever the data doesn't need to persist, and pack what must be stored. What is the transfer or send gas stipend problem? Earlier, whenever you made use of either transfer or send function, it forwarded a hard-coded 2300 gas stipend. Now this was used as a safety feature. The 2300 gas was used as a safety feature. So this was just enough for a simple log event, and it was on purpose kept too small to make a further state changing call, or imagine this to be an early anti-re-entrancy measure. However, what problem do we face with this hard-coded 2300 gas stipend value? The stipend is fixed. This 2300 value is fixed. It cannot be changed. However, the opcode gas costs are not. Now this leads to EVM repricing, which can make the 2300 gas too small even for a legitimate recipient. What problem one can face? The practical failure mode is the recipient can be a contract having a non-trivial receive or fallback function. In that case, since the 2300 gas is too less, this can make the contract permanently unable to receive funds. So this is the gas stipend problem. In order to overcome the gas stipend problem, what is the modern recommendation? This we have already covered while we were discussing the reentrancy hack or the DAO hack. The modern fix is use check effects interaction pattern. Use check effects interaction patterns in which first you do the checks, then you update the state, which are also known as effects, and then at last you make the external interaction or forward all remaining gas. So this is the fix to the transfer or send gas stipend problem. Call value, what it does, it forwards all available gas. In this case, there are no hard-coded stipend to become stale. However, this also removes the accidental reentrancy guard of 2300 gas used. So, the check effects interaction pattern becomes mandatory. Since we are making use of call, it forwards all the available gas. Since it forwards all the available gas, hence the possibility of reentrancy arises. In order to disable the reentrancy possibility, one must make use of check effects interaction pattern. This disables the reentrancy pattern. And also, always check the Boolean return value. Unlike in case of transfer or call, it does not revert automatically on failure. It returns a Boolean value OK, which you must check explicitly. If it is false, then the transfer has failed. Storage packing in Solidity. The size of storage slot is 32 bytes. The EVM organizes contract storage into 32 byte slots. Solidity automatically packs consecutive small state variables into the same slot. For example, imagine this is a 32 bytes storage slot. Now inside this storage slot, we are storing a value of type uint8, a value of type uint64, and another value of type uint64. uint8 takes 1 byte, uint64 takes 8 bytes, again uint64 takes 8 bytes. So in total, these three values take 9 bytes. And these 9 bytes are stored into a single storage slot. So one 32 byte storage slot, it is packed with 3 small variables instead of using 3 separate slots. One thing to remember, packing only helps when variables are declared adjacently. That is, if you would have declared uint256 and after that you would have declared uint64 and again after that you would have declared uint256 and again uint64. In that case, Solidity would have used 4 storage slots because the 2 uint64 were not declared adjacently. What does it mean? Whenever you have fewer slots written, that is equal to fewer SSTORE operations. So this directly reduces gas cost. Since SSTORE opcode is the EVM's most expensive operation class, what you have to remember is whenever there is a variable having a data type that can be packed into a single storage slot, always define those variables adjacently in your Solidity smart contract. Let us take a look at storage packing in practice. Here, inside the struct position, we have defined first amount whose type is uint256. Converting uint256, we come to know that it takes the entire 32 bytes. That is, the slot 0 is full. Then we have uint8. So uint8 takes only 1 byte. This goes into slot 1 and the remaining 31 bytes is wasted. Then we defined opendat whose data type is also uint256. In this case, it goes into slot 2. So here we see a position structure which makes use of 3 storage slots. Now let us have a look at how can we pack this together. We are using the same struct position. Since amounts type is uint256, it is anyway going to take the entire storage slot. So slot 0 is full. Then we change opendat from uint256 to uint64. Since opendat will be a timestamp and timestamp value can be successfully represented using uint64. Now this goes into slot 1 and it shares slot 1 with uint8 leverage because opendat now takes 8 bytes and leverage takes 1 byte. What exactly is happening? First, this goes into slot 0. This goes into slot 0. Then we have our slot 1. Now inside slot 1, the first 8 bytes is taken up by opendat. Then the next 1 byte is taken up by leverage. And these remaining bytes are kept empty. So ideally what we have done, we have changed our opendat data type from uint256 to uint64. By doing so, we have brought down the storage slot from 3 to the value 2. This is storage packing in practice. Let us recap today's decision checklist. Whenever there is a precondition that fails, how can you inform the caller about that? In that case, make use of require or revert with a custom error. Whenever there is an internal invariant that should always be true, in that case, make use of assert. Whenever you are sending ether to an address you don't fully control, make use of call and follow the check effects interaction pattern and never use transfer or send directly. Then at last, if there are multiple small state variables declared together, check whether reordering packs them into fewer slots. Fewer storage slots leads to fewer storage writes. That leads to less gas consumption. That leads to less transaction cost. So what we have covered today, we have talked about require, assert, revert. After this, we looked into custom errors, how to define custom errors, and how to throw custom errors from within the smart contract. Then the 2300 gas stipend problem in case of transfer and send, and at last the storage packing. In next lecture, we are going to talk about secure access control, including the ownable pattern and the role-based access control pattern. And at last, we will look into events with indexed parameters and how that can be used for off-chain monitoring. So before Friday's lab, all the students must review the checks effects interactions example because that example you are going to extend it into the hard hat testing assignment. That wraps up this session. If it helped, like and subscribe so you don't miss the next one. Questions? Drop them in the comments below. See you in the next lecture.